Hi, welcome to another video note for Operating Systems Internals and Design Principles by William Stallings. My name is James Craig Burley. This is the video note for Figure 5.4, a definition of binary semaphore primitives. In contrast to the code for Figure 5.3, this code implements a binary semaphore. In place of the count in the binary semaphore structure, we have a value that is really just a bit value. It takes one of two values, 0 or 1. And the wait operation is different, only that it checks whether the value is already 1. If it's 1, it sets the value to 0, because that means that one process is able to wait on the semaphore without blocking. Otherwise, it's very similar to the case. In fact, it's identical to the case that we have for the wait operation in a counting semaphore in Figure 5.3. The current process, or the process on behalf of which semaphore wait B, or sem wait B is called, is placed in the queue, the semaphore's queue, and then the process is blocked. And for more details on what that means, do review the video note for Figure 5.3. Sem signal B is a little bit more different than sem signal, the counting semaphore version, in that it doesn't start off by referencing the count. It examines the queue itself, and if the queue is empty, that means that there are no processes that are waiting on the queue, waiting on the semaphore, and the value is simply set to 1. It doesn't matter if it's already 1, and if it's 0, then we set it to 1, because 0 means that no further processes may wait on it, but signaling it will now put it into a state where a process may wait on it without being blocked. If the queue is not empty, again, this code here is very similar, or basically identical, to the corresponding code for the counting semaphore in the sem signal routine. We remove a process from the queue, and we place the process on the ready list. One of the main differences in concept between binary semaphores and counting semaphores is that the count of processes that are waiting in the queue is not duplicated between the count value in the semaphore itself and the queue itself. That is, there's no redundancy between the queue and the value, because the value doesn't contain a count. So with the binary semaphore, the queue is more important in terms of the determination of whether the semaphore is ready to fire off a process. An advantage of the binary semaphore is that there needn't be a strong discipline when it comes to overly signaling a semaphore. That is, a signal can be viewed as a method of saying that the resource in question being protected by the semaphore is available without having to worry that doing too many signals means that there would then be waits that would proceed when in fact the resource still is needed. This distinguishes between a situation where the semaphore protects a number of elements in an array, or let's say a FIFO or a stack, versus a single shot resource. In most cases where semaphores are used in practice, the semaphore's initial value is either 1 or 0. It's 1 if the resource is considered to be ready to use, and 0 if it's not yet ready to use, and it would have to be waited upon. Theoretically, a counting semaphore could be used to protect a FIFO structure, such as a buffer, and initialized to the number of entries available in the FIFO, so that each wait reduces that number, but doesn't actually cause a wait until the number has reached 0, meaning that the buffer is now full. Similarly, a signal could simply be called every time an item is removed from the buffer. That usage is actually somewhat rare for a variety of reasons. One is that the semaphore operations, wait and signal, are usually a little bit too expensive to use in the kind of tight inner loop that would be employed when filling and emptying a FIFO. So the advantage of using the binary semaphore is that you simply signal when you have made available the resource in question to others, and if it so happens in the same code path or in another process, signal is also being called again, it still only has the value of 1 in terms of the semaphore itself. It's not going to have a value of 2, and thus allow two processes to access that one resource at a time by doing two waits, both of which proceed. This is a useful characteristic of a binary semaphore. One way to look at the difference between a binary and counting semaphore is that the binary semaphore uses the queue as a kind of count, and the empty queue with a value of 0 corresponds to an actual empty queue, whereas the empty queue with a value of 1 in the semaphore, in a sense, corresponds to a negative queue, a queue with -1 processes waiting in it. And that's a situation where when a process then goes to wait on the semaphore, because there's -1 processes waiting in it, that process is able to continue right away without being added to the queue.